Hi, so I want to thank the organizers for inviting me to talk and for organizing this very nice conference. I'm learning a lot of things so far. So as John said, I'm going to be talking about renormalizable rectangle exchange maps. And they're kind of a discrete dynamical system. OK, so here's an outline of my talk. I'll explain the main results, and then I'll give some background about the kind of systems that I'm looking at. And then I'll explain how to use cut and project sets to construct domain exchange maps, or DEMs for short. Then I'll specialize the construction to a particular family called PV-DEMs. These are short for Piezo-Vijayaraghavan domain exchange maps. They're related to a particular kind of algebraic integer. And for these, we'll develop a renormalization scheme. That's a way to speed up the dynamical systems. And then I'll talk about multistage REMs. So that is a way to compose different maps in the family. And that leads to a more complicated renormalization sequence. And then I'll talk about some future work. So I just want to mention this is all joint work with Rick Kenyon and Rani. It's on the archive, and it will appear soon in ergodic theory and dynamical systems. OK, so this is the dynamical system I'm going to be studying. It's defined on a smooth Jordan domain. So you could just take here, for example, we've taken the disk of radius 1, and my dynamical system, capital T, is a map from the disk to itself. And it's a piecewise translation. So on the right here, I've drawn the disk in the forward orbit of this purple point here. And the disk is cut up into pieces, and on each piece, the map is locally constant. So every time the point, for example, every time it returns to this tile, the map just translates it by the dark blue vector. Okay? And then you can follow the orbit around. Now, this is a very simple dynamical system, but it's also very discontinuous. And it's these sharp discontinuities that make the system so complicated. Okay. Now, if you think about it a little bit, you can see that you can encode everything about the dynamical system with two different tilings of your domain. So on the left here, I've drawn the second tiling, and it tells us where every tile in the domain gets translated. So if we want to know where points in this region end up, we can just look over here and find the corresponding region. It's over there, and they'll get translated by the vector that, well, moves this piece up there. OK. So you can also describe it a bit more formally with two different partitions of your domain X. You can write it as a union of AK and as a union of BK, which are translation equivalent, meaning that for each k, there's some vector vk in R2 with ak plus vk equal to bk. And then we define the domain exchange map T of x is just x plus vk, where the vector vk is associated to the tile ak. Okay. And then we'll leave it undefined for points on the boundary. Any questions about the setup here? All right. So before I can tell you the
map on the disk.
How did we find it? So if you
obviously there is such a thing on the disk.
Yeah, so that's an interesting point. What Rick's mentioning is we've taken our disk, cut it up into pieces, and rearranged the pieces so that we get back a disk. And it's not really obvious that you can do that. And to show that you do it, you can do it. You'll have to use the construction that I'll tell you about a little bit later.
You need a compass, right?
Huh?
You need a compass.
A compass?
Yeah, because every edge of the piece has to be an edge of the disk, right?
Yeah.
So.
Yeah, but the pieces are translated. Right.
Right.
Right. Yeah.
So the question is, where are the centers of circles where you have to?
Exactly. Yeah. Okay. Okay. So the first property that we're interested in studying about these dynamical systems is that of minimality. So this is this kind of describes the behavior of the orbits in a very general sense. And we say that a dynamical system is minimal if every point has a dense orbit in the domain. Okay. Now, to study more refined properties of the orbit, we want to understand the first return map. And this I've called t hat restricted to y. And it's a map from a subset y of the domain to itself, defined as follows. We take a point in y, and we're going to follow the orbit of the point along until the first time it returns to y. That gives us a new dynamical system, t hat. And this is called the first return map. It's a way to speed up the dynamics. And so if you can compute this, you can compute the sped up dynamics of the system. But it's usually quite hard to compute. You can write it down for a particular example. You can do a lengthy computation and find this first return map. But I'll present a large family of them for which we can explicitly write down the first return map. Okay. I'm also going to specialize to the case where the domain is a square. So before I showed you the case where the domain is a disk. But we'll specialize to that case. And then the tiles are going to be rectilinear for the reason that this gentleman was pointing out. And so we call it a rectangle exchange map, or REM. Okay. And the tool we'll use to compute this first return map is what's known as a renormalization scheme. So it's three different things. It's basically a new dynamical system T prime from some other domain x prime to x prime, which allows us to compute the first return map by just taking one step of this new dynamical system. So we fix a proper subset y of the domain, and the first return map to y will be conjugate by phi, where phi is some homeomorphism, to this other dynamical system T prime. Okay, so we can just evaluate the first return map by taking a point, mapping it to this other domain x prime, applying one step of T prime, then mapping back to y. Now, in some cases, this second dynamical system T prime will actually be equal to T. And then you can iterate this procedure of taking first return maps. And you can compute longer and longer term behavior of the system. And in that case, we call the system self-induced or renormalizable. So we have three main results. We give a method for constructing minimal domain exchange maps on any domain, which have equidistributed orbits. That's equidistributed with respect to Lebesgue measure. And then we find an infinite family of renormalizable REMs. So meaning that we've found a renormalization scheme for an infinite family of these. And then we compose certain of these REMs to produce a 4-parameter family of multistage REMs. And these are going to have more complicated renormalization schemes. So they're no longer self-induced. You'll have to apply a sequence of different renormalization schemes before they come back to the dynamical system that you started with. OK, and I'll explain more about this later. All right. So I just want to mention some background about the area. So these DEMs that we're studying are generalizations to 2 dimensions of a well-studied one-dimensional object called an interval exchange transformation. And you could think of that as just a domain exchange map defined on an interval. You could also think of it as every IET can be associated to a probability vector and a permutation. So you just take your interval from 0 to 1, you chop it up into pieces, and you you rearrange them, and that defines an IET. So these are important examples in ergodic theory. And in 1975, Keen discovered a criterion for when these are minimal. That means when the orbit of every point is dense. But a little bit later, in 77, Keen discovered that you could build an example of these with just 4 pieces, where, which are minimal but are not uniquely ergodic. And what that means is that the orbits of points are not equidistributed with respect to Lebesgue measure. All right. But this is a rare situation. And in 82, Major and Veach showed that almost every minimal IET with an irreducible permutation, meaning that it kind of mixes up the interval sufficiently well, is actually uniquely ergodic. More recently, Chayk and Major computed the Hausdorff dimension of the set of non-uniquely ergodic IETs with n pieces. And they showed that's n minus 1 minus 1/2. And one thing that they used in their proof was Rousey induction. And this is a general or a renormalization scheme for essentially any kind of IET. And Rousey induction does not generalize to 2 dimensions, unfortunately. So when we started this project, we wanted to find some kind of renormalization theory for 2 dimensions, for 2-dimensional domain exchange maps. And the hope is that with this we can understand the ergodic properties of this dynamical system. Okay. All right. There's been a little bit of previous work on domain exchange maps. In 1981, Haller generalized Keen's minimality criterion to 2 dimensions, but becomes very difficult to verify or to verify this condition in practice for these 2-dimensional objects. And in 2013, Pat Hooper discovered a 2-dimensional family of renormalizable REMs, but his are going to be different than ours. His had points with periodic orbits, whereas ours are going to have minimal orbits. Okay, there's also some work by Rich Schwartz, and he used multigraphs to construct what he called polytope exchange transformations. And these are generalizations of domain exchange maps to higher dimensions. And he looked at a particular class of these called octagonal pets, and he developed a renormalization theory for those. Okay, and Ragny also looked at a family of she called renormalizable triple lattice pets using this method of Schwartz. Okay, so our goal was to find a large family of minimal domain exchange maps and to develop their renormalization theory. So now I'll explain how we can use cut and project sets to construct these DEMs on any smooth Jordan domain. Okay. So we take a lattice L in R3, which is full rank, and we're usually going to want it to be some kind of irrational lattice. And we'll take X to be a domain in the XY plane. Then lambda of XL, this is going to be a set of lattice points which you can sort of see through your domain X. So that's what I've drawn here. You can imagine that X is a square sitting in the XY plane, and we're looking through X at the lattice, and we only see certain lattice points. So these are going to help us construct the domain exchange map. And we need these set of points in the window, well, I'll call that lambda of XL, to have a certain property. And the property is that when you take these points and you project onto the orthogonal direction, so here I'm thinking about X as lying in the XY plane. There's an orthogonal direction in the Z coordinate. And, well, pi Z of P means that we project those points onto the Z direction. Then we want that set of points, P, to be injective and the projection to be dense in R2. So it's kind of what you see here. If you look through your window X, you see a dense set of points. And if you rotate it by 90 degrees, if you imagine rotating this whole window, you'll see points which are spread out, and their z-coordinates are going to be a discrete set. Okay, so what you will see is something which looks like this picture, where you have a point here, point there, point there, point there, and then you kind of go. Okay. And we'll use this sequence of points that are in this tube here to define our domain exchange map. So these points in the tube are naturally ordered. And they're ordered just by their z-coordinates. And so this point has a z-coordinate which is smaller than that point. And then there's a next point with a slightly larger z-coordinate over here. And as you can see, they're all ordered. And so we can define a dynamical system on lattice points in this window, which I'll call T tilde. And T tilde of xi just maps it to the next point in this ordering, okay, which is exactly the picture here, where if I take a point here and I apply T tilde to it, well, I just end up there. And because our set of lattice points forms a cut and project set, there are going to be finitely many interpoint vectors. So if you look at the vector between this point and that point, and then you look at the vector between this point and that point, there are only going to be finitely many of them. We call these translation vectors, and I'll label them by eta I. And we take these translation vectors, eta I, and we project them onto the xy plane. So here I've taken vi to be the projection of eta I onto the xy plane. And those translation vectors are going to be used to give us the translation vectors for the domain exchange map. And one important property is that these vectors come with an ordering that they've inherited from the fact that in lambda of xl, each vector has we can project these onto the z-coordinate. We can find the lengths of the projection onto the z axes. And so we'll just order them by those lengths. OK. All right. So we have to show that that this map T that I've constructed in this way is actually a domain exchange map. And if you go back and you sort of look at this picture, and if you look at the earlier picture over here, it's kind of clear why it will be a domain exchange map, right? So I've colored it by points. So every point with the same color here will get translated by the same translation vector. And you can already see that this is basically going to give us a tiling of x. Okay? But to actually find the tiling, what we do is we take our domain x, okay, and we're going to translate it by a negative v0, where v0 is the smallest vector in this ordering coming from the projections of the translation vectors in T tilde. And so when you translate it, you get you move your square over here, and you can intersect that with this first square, and you get this small green region A0. And that will be the first tile in our partition of the domain exchange map. And then you keep going. So you translate by the next vector, which is negative v1, and you intersect with your original domain x. You get this light blue region. That will be rectangle A1. And you just keep going. There's some issue which can occur, as you see in this next picture, where we've translated by negative v2. And the issue is that you can translate and intersect, and your intersection covers areas that you've already covered before. And so what we just do is we say, OK, if an area has already been covered, we'll exclude it from that set. So the region that gets translated by this, the vector v2, this dark blue region is just those two squares. So one thing you see is that the tiles in the partition are going to be rectilinear. And if you keep going, you will end up with something, a partition of the square. And here I've drawn an example that we'll get to later where the partition looks roughly like this. OK. All right. Any questions? OK. So the first theorem we proved was about the orbits. And we showed, and there's a very helpful comment from the referee about this theorem, that every well-defined orbit is dense and equidistributed in our domain X. And you can see that by relating our dynamical system T to the first return map to X on a particular torus. The first return map of the vertical linear flow on a torus. So we're going to imagine our domain X as sitting in the torus R3 mod L. And I here is just the inclusion map from X into R3 mod L. Then phi t, this is going to be the flow in the z coordinate. So it will just be x, y, z plus t mod L. And tau p, this is the first time when the flow returns to the domain X, which we're thinking of as sitting in our torus. And if you think about the construction of our domain exchange map, you can see that T is just conjugate to the first return map of the vertical linear flow on the torus. And we know by Weyl's equidistribution theorem that orbits of the vertical linear flow are dense and equidistributed. And so therefore, when the orbits of our dynamical system will also be dense and equidistributed on X.
Sorry, I missed it. How do the non-well-defined orbits come about? How many?
Yeah, that just comes about if you end up hitting one of the boundaries of the tiles. So that's all. OK. Any other questions? All right. So now I want to explain how we can specialize this construction to create domain exchange maps which are renormalizable. And the way we do this is to use a certain algebraic structure of the lattice. And we need these certain algebraic integers called piezo-Vijayaraghavan, or PV numbers. And a PV number is a real algebraic integer, so just a root of a polynomial, with modulus larger than 1, whose Galois conjugates have modulus strictly less than 1. So as an example, you could just take this polynomial here, x cubed minus n plus 1 x squared plus nx minus 1 equals 0. And if n is greater than or equal to 1, the leading root is a PV number. OK, so this family of polynomials is going to give us a family of domain exchange maps which are all renormalizable. And let me explain how to do that. So we'll use this PV number. So let lambda equal lambda 3 be a PV number whose Galois conjugates are real. And our lattice is going to be the Galois embedding of z adjoin lambda into R3. And you can just think about your lattice X as being generated by these three vectors, 1, 1, 1, 1, lambda 1, lambda 2, lambda 3, lambda 1 squared, lambda 2 squared, lambda 3 squared. Turns out with this lattice that lambda of XL will always be a cut and project set. Okay. And at certain times in this talk, we're going to want to identify points with their integer coordinates. And we can identify z adjoin lambda with z3 by just saying that a triple of integers a, b, and c gets mapped to a plus b lambda plus c lambda squared. And then we can take this point, and it just gets mapped into R3 by these projections pi xy and pi z. So if I have a lattice point a plus b lambda plus c lambda squared, its xy coordinates and z coordinates are just given by these three equations. Okay. So we say that a PV DEM is a cut and project DEM associated to the Galois embedding of a PV number with real Galois conjugates. Okay. All right. So we're going to specialize to the case where the domain is a square of unit edge lengths. So as I mentioned before, the tiles will be rectilinear. And so the domain exchange maps we call REMs. Okay. And we're going to look at a certain family of PV numbers. And it's easier to think about these as eigenvalues of a certain family of matrices. And these matrices here are going to come up later when we talk about the renormalization scheme. Okay, so I'll just take S to be the set of matrices Mn, which are 0, 1, 0, 0, 0, 1, 1 minus n, n plus 1. And we'll need n to be at least 6. If n is greater than or equal to 6, you can show that the eigenvalues of this matrix, the smallest two are between 0 and 1, and the largest one will be bigger than 1. So the leading eigenvalue is a PV number. And this is going to give us expansion in the z direction and contraction in the xy plane, which is eventually going to lead to the renormalization scheme. So we showed that for any matrix Mn in this family, if you take the PV REM associated to it, then they all have the same combinatorics. Okay, so here I've shown two REMs with the same combinatorics. So this top panel, these top two figures, show two different partitions of the square. Okay, and they tell us everything we need to know about the map. And here I've shown a different REM with the same combinatorics, meaning that it has the same number of tiles. They're in roughly the same locations, but the tiles could be stretched horizontally or vertically. Okay. All right. And once you prove that, you can explicitly write down the coordinates of the tiles. What they are is not so important. It's just interesting to observe that the coordinates are actually linear combinations of, they're algebraic integers in z adjoin lambda. Okay. All right. So for these PV REMs, we're able to develop a renormalization scheme. And this picture here explains the renormalization scheme. So if you take this REM, and it's associated to the matrix M6. And now you look at the first return map to this green rectangle 0, which I've called A0. So that is a new dynamical system. And it will be, again, a domain exchange map. But it turns out for this family that this new domain exchange map is just a scaled copy of the original one, meaning it has the same number of tiles. And the tiles, they're just going to be kind of shrunken versions of the original one. So this is quite remarkable because if you follow around the orbit of a point and you try and compute the first return map that way. So for example, if we take a point which lies in this portion of the rectangle 0, so maybe we take a point which is going to lie over here, its orbit could be very complicated. And so this green region in the first return map gets subdivided into separate pieces, and they all travel around the domain, and different pieces will take different number of steps to return back to our set, to return back to this set Y. Okay. But they all come back together, and then they form this very nice first return map, which is just a scaled copy of the original one. Okay. Right, so our theorem is the renormalization scheme for domain exchange maps in this family. And so we take a matrix M and S. As I mentioned, it will have eigenvalues where the smallest two are between 0 and 1, and the largest one is bigger than 1. We take, we call Tm the associated PV rectangle exchange map. And we'll take Y to be the tile in the partition corresponding to the rectangle 1 minus lambda 1, 1, comma, cross 1 minus lambda 2, 1. So if you go back to this picture, we're always going to take the first return set to be this rectangle in the top right, okay, which I've called rectangle 0. And so Tm is renormalizable, where the first return map can just be written as phi inverse composed with Tm composed with phi, where phi is an affine map computed explicitly here, and the formula just depends on the eigenvalues. xy gets sent to x plus lambda 1 minus 1 over lambda 1, and y gets sent to y plus lambda 2 minus 1 over lambda 2. So this is the affine map, which takes our whole domain x and scales it, and then translates it so that it fits into this smaller rectangle in green at this top right corner. Okay. All right.
Sorry. Lambda 1 and lambda 2 are less than 1.
Lambda 1 and lambda 2 are less than 1. So phi is an expanding map, exactly, so the inverse of what I said. Yeah. Thank you, Rick. Yes. Yes. Good point. Okay. Okay. So I want to make a few comments about the proof. And the proof uses the algebraic structure of this lattice. So just to remind you, lambda of xl, these are the set of lattice points which lie in our window that we can see through x. Okay, and I'll call lambda sub y, those are the set of lattice points which lie in the window, but which lie in a smaller window that we can observe by looking through this first return set. So I have a big window, which I'm using to look at all these lattice points. And then I have a smaller window where the first return set lies. And it turns out that you can define a bijection between the points in lambda of xl and lambda of y. And you use this matrix Mn, which is an integer matrix, which I mentioned before. So if we take a triple of integer points a, b, and c, then it just gets mapped to Mn transpose applied to a, b, c, plus this translation 1 minus 1, 0. And what this map does is it sends all of the lattice points that you can see through this big window into the lattice points that you can see through the smaller window. And this preserves the ordering of the lattice points in lambda of xl. Okay, so what that means is below. So if pi z of omega I, right, the z coordinate of omega I is less than pi z of omega j, well then, when I use my bijection psi to map this into lambda y, and then project it onto the z-coordinate, it'll be less than pi z composed with psi of omega j. Okay, so what this tells us is that if I want to compute the first return map to this green rectangle, well, I can just essentially map my original dynamical system that was this t tilde thing that was defined on this lattice lying in R3. I just map those points into my smaller window. That's going to give me a bijection. So therefore, I can use this map psi here to compute the first return map. So this is really nice because it's essentially a computational you don't have to do any computations to compute the first return map. Okay, and the same proof works for any domain exchange map in this family. All right. Okay, so now I want to explain how we can combine rectangle exchange maps in this family, or compose them to form multistage REMs. And these are going to have renormalization schemes which are no longer kind of one step. So if you think about before, we found a renormalization. We said that the first return map was going to be conjugate to the original dynamical system. Well, now I'm going to have a sequence of dynamical systems in that first return, in that renormalization scheme. And we're able to combine these. I'll get to that in a little bit. But we're able to combine them to form a four-dimensional parameter space of multistage REMs. So here I've drawn the four-dimensional parameter space of these rectangle exchange maps. And, well, every point in here is associated to a rectangle exchange map which is renormalizable. It might, there might be a sequence of renormalization schemes, but eventually it will be renormalizable. And if you take a nearby point, which is not in these set of colored points, well, then it will no longer be renormalizable. So you can compute the first return map, but the combinatorics of it might change. Okay. And our conjecture, which we weren't able to prove, is that the closure of the parameter space of renormalizable rectangle exchange maps is a Cantor set in R4. Okay. And the key lemma that we need to build these REMs is to expand our set of matrices. So before, we just looked at the set of Mn, where n was at least 6. But now we look at the monoid of matrices generated by S under matrix multiplication. We'll call that M. And it turns out that for any matrix in this monoid, its leading eigenvalue is a PV number. And in particular, if you order its eigenvalues, then the two smallest ones are between 0 and 1, and the largest one is bigger than 1. Okay. And because the leading eigenvalue is a piezo number, this is sometimes a matrix with this property, sometimes called a piezo matrix. You might call this a piezo monoid. Okay, so I just want to make a few comments about the proof. So you can use the Perron-Frobenius theorem to show that the leading eigenvalue is bigger than 1. And you can use it again on the inverse of the matrix to show that the smallest eigenvalue is bigger than 0. So the real difficulty is showing that the second eigenvalue is smaller than 1. And just to remind you, we need this so that the dynamical system will have the right expansion properties, so that when we try and compute the renormalization and we end up applying this matrix Mn, we need it to shrink along the x and y directions and to expand along the z directions. So to show that the second eigenvalue is less than 1, you look at the characteristic polynomial, and then it turns out that it's equivalent to showing that the coefficient b of p in front of x is less than the trace of p. And we use an inductive argument to show that, where we write our matrix in the monoid as a product of these generators of the monoid of length n, and then we use induction on that product. Okay. All right. So only certain REMs are going to, we're only going to be able to compose certain REMs. And the reason is that the combinatorics can sometimes change. So we say that an REM is admissible if it has the same combinatorics as the family of PV REMs associated to S. So I'm taking these rectangle exchange maps that I showed you before, and I want to look at other ones which have the same combinatorics. Okay, but we're going to enlarge the family by generating new lattices using these new matrices Mn, which are in our monoid S. So first we take L to be the Galois embedding of the eigenvalues of Mn, which is just lying in S. And we take epsilon to be the translation in vectors associated with the dynamical system T tilde of Mn. So back before when I said that all of the matrices Mn would give us REMs with the same combinatorics, essentially what that's saying is that these translation vectors, that the integer coordinates of these translation vectors are all going to be the same. So we can just fix this set once and for all, script epsilon, to be those 7 translation vectors. And then what we're going to do is we're going to project them onto the xy plane with kind of funny projections. So I take my matrix W in the monoid, and I take the eigenvectors xc1 and xc2 associated to the eigenvalues lambda 1 and lambda 2, and I normalize them so that their first coordinate is 1. And now I use this projection pi xy, which maps a point x to x dot xc1, comma x dot xc2, to define these translation vectors above vi, which are going to be the translation vectors for my new rectangle exchange map. Okay, and then I build it as before, where I just take my domain and I shift it around by all of these vectors. So we say that this new rectangle exchange map associated to the matrix W in my monoid is admissible if it has the same combinatorics as T sub Mn. Okay. And again, if it's admissible, you can write down formulas for the tiles. They're not so important, but they are linear combinations of the entries of these eigenvectors, which is similar to what we saw before in the single stage case. Okay, so a theorem is that the admissible REMs are minimal, and it's essentially the same proof as before. So I won't say much about that. Okay. Now we want to look at cases in which this admissible REM has a renormalization scheme to it. So what we do is we take a matrix W in my monoid, and I'll write it as the product of L of these matrices, M sub n, and TW we'll assume is an admissible REM. And now I'm going to use the eigenvectors c1 and c2 of W to define projections onto the xy plane, which are going to give me the translation vectors of each REM in my sequence. Okay, so I take okay, so I have to define these partial products. W1 is m sub n1, W2 is mn2 times mn1, and so on up to W, which is just WL. It's a product of all of them. And then I apply WK to Xi, and I get some new vector Xik. And I'm going to use those to get my projections pi k xy, which just sends x to x dot c1k, comma x dot c2k. And for each k, by projecting these translation vectors a to I under pi k xy, I'll get a set of translation vectors which give us a new rectangle exchange map. And we call that TK. That's the rectangle exchange map with the translation vectors in VK. Okay? And we say that an admissible REM is a multistage REM if this sequence of REMs, T1, T2, all the way up to TL, all have the same combinatorics. And we need them all to have the same combinatorics so that each renormalization is going to give us, so each first return map in the renormalization sequence will have the same combinatorics as what we started with. And the theorem is that if you take a multistage REM TW, then it's renormalizable. And the first return map can be computed by just taking one step of this new dynamical system, TK plus 1. So it's a little easier to understand with this picture here. OK, so I take my matrix W, which is M7 times M7 times M8 times M6. And with that matrix, I'm going to build a rectangle exchange map using my method. And it turns out that the tiling is exactly this. Okay? And now, if you look at the first return map to this light green rectangle, you'll get a new rectangle exchange map. And it turns out that it has the same combinatorics. And if you check, what turns out is that you get a scaled copy of this next rectangle exchange map. So what I've done is I've taken my first return map here and blown it up, and so I get this picture, which is a new rectangle exchange map with the same combinatorics. And now I look at the first return map again to this green rectangle, and I blow that up, and I'll get this dynamical system here. Okay? And I repeat. I look at the first return map here, and I get this rectangle exchange map. And then when I look at the first return map again to this small rectangle, I get back a scaled copy of the rectangle exchange map that I've started with. So W here was a product of 4 matrices. And that means that in this sequence, you'll have 4 different rectangle exchange maps in the renormalization sequence. OK, and each homeomorphism, phi k, is an affine map, which you can write down explicitly. And it's explicit in terms of the eigenvectors of the matrix W. And I'm running low on time, so I will just skip this and skip this. And I will just mention that what we're very interested in studying is the 4-dimensional parameter space of multistage REMs. So here, this is the picture that I showed before. Every point here gives you a multistage rectangle exchange map. And there are various interesting questions that we are studying about this parameter space. Okay, thank you.